Hello and welcome to the presentation of our paper titled Exploring Time Series Imaging for Load Disaggregation. My name is Hafsa Bousbiat and I'm a computer science engineer, currently enrolled as a PhD student at the University of Klagenfurt within the Dataset research project. So the Dataset research project is an interdisciplinary research project composed of economists, psychologists, and also people from technical sciences gathered with the same goal of investigating new ways of supporting human decision-making in digital environment. And one of the main research questions that interest us is how can the quality of decisions be secured under the diverse support of digital technologies like smart meters and load disaggregation, which will be at the center of our talk today. The main task of load disaggregation is to identify different appliances' contribution in the total power consumption of a household. And to achieve this, many approaches in the literature adopt the sequence-to-sequence mapping coupled with deep neural networks that gained more and more attention in the last few years. However, despite the fact that these models provide decent performance, scholars still stress the need to enhance this aspect. And one way to do this is to look beyond the one-dimensional representation of the input time series sequence. If we look at the literature, we can already identify several approaches that use this idea of time series imaging to look beyond the one-dimensional representation, but with different transformation. And unfortunately, no work comparing between these transformations and their effect on the performance. This fact lies at the center of our work, where we want to answer two main research questions. First, what are the existing image transforms for time series? And second, we want to identify the most promising image transform in the case of load disaggregation. So, what time series imaging is? Well, it consists of a set of approaches that takes as an input a one-dimensional time series and gives as an output a two-dimensional representation encoding the dependencies between each two instances within the input sequence. During our study, we selected three common algorithms for time series imaging: Gramian angular summation field, Markov transition field, and recurrence plot that we will explain more in detail in the next few slides. So the first representation is called Gramian angular summation, and it gives as an output a square image representation that preserves temporal dependencies as the time increases with the positions from the top left corner of the image to the bottom right corner. The construction algorithm goes through three steps. It starts by first doing a min-max normalization of the sequence, then representing it in a second step in the polar coordinates to finally calculate the cosine function of the sum between each 2 points and encoding this in a matrix. The second representation is the Markov transition field, which gives as an output images that consist of transition probabilities. The construction algorithm starts by identifying the Q quantile bins of the input sequence and assigning each element of the sequence XY to the corresponding quantile. The final MTF representation will then be a matrix whose elements MYG will represent the probability of transition from the quantile relative to the value XY to the quantile relative to the value XG in the input sequence. The third representation is a recurrence plot, which gives as an output a binary representation of the similarity measure between each two instances within the input sequence. In our work, we consider the Euclidean distance as similarity measure between the values. The construction algorithm starts by calculating the distance between each two instances within the sequence, and then subtracting a predefined threshold from each calculated value to transform this finally to a binary representation using the Heaviside function. For more clarity about the differences between the three algorithms, we provide an example of three image representations of the same power window of data provided by the smart meter. As we can see, the three representations provide different images, and our goal in our study is to identify which one of them will help the network to gain better insights about the appliance's consumption patterns. To compare these three image transforms, we augmented the well-known sequence-to-sequence pipeline with an image representation in such a way that each input sequence is transformed into its two-dimensional representation before feeding it to the network. Our goal from extending an existing pipeline was first to measure the performance gain of the two-dimensional representation over the one-dimensional representation, and second, to compare these three image transforms on the same setup. So, to have a fair comparison between the one-dimensional pipeline and the two-dimensional pipeline, we adapted the autoencoder architecture already proposed in the literature, and that employs a sequence-to-sequence strategy. The autoencoder first encodes the input to a compact vector representation, and then decode this representation to reconstruct the target consumption. The architecture is composed of one-dimensional convolutional layer as an input layer, which we change into a two-dimensional convolutional layer in the case of our pipeline to take into consideration this new representation of the images. The convolutional layer is followed by three dense layers and an output layer. To obtain more generalizable findings, we considered data from three different energy consumption datasets: Refit, Cindy, and UKDAL. For one household per dataset, we selected 4 common household appliances: the dishwasher, the fridge, the microwave, and the washing machine. We extracted a subset of 105 days, which we split into 90 days to serve as training set and the remaining 15 days to evaluate our algorithms on. We applied a sampling rate of 10 seconds throughout our investigation. In accordance with previous studies, we set the input time window to 20 minutes for the fridges and the microwaves, whereas we selected the time windows of 30 minutes for the dishwasher and the washing machine. We employed two metrics to measure how well the disaggregated data resembles to the actual power consumption. The first one is the mean absolute error that quantifies the error predicted at every time point. And the second one is the normalized disaggregation error, which measures the normalized error of the squared difference. The current slide presents the results on the first dataset, where each graph refers to a metric. In each graph, the y-axis records the value of the error and the x-axis contain different appliances. For each appliance, we report the error relative to different algorithms. During the evaluation, we used the factorial hidden Markov model, which is a probabilistic approach, as a benchmark, and the denoising autoencoder as a one-dimensional baseline to which we compare the proposed pipeline. So the results on this first dataset show that the denoising autoencoder, as well as the proposed two-dimensional pipeline, outperformed the factorial hidden Markov model in all cases. We also observed that the two-dimensional representation provide an enhancement in the performance, especially in the case of the fridge, where we observe a huge improvement between the denoising autoencoder and the two-dimensional pipeline. Exception to this trend is the dishwasher, which provides better results with the one-dimensional denoising autoencoder. As for comparing between the three imaging algorithms, we notice that the Gramian angular summation field provides better results in most cases, though recurrence plot could also be a viable alternative in some cases, like the washing machine. The results on the second dataset show that there is the same trend, exception for the dishwasher, where the two-dimensional pipeline outperforms the denoising autoencoder. The last dataset shows the same trend as the first dataset, where the denoising autoencoder this time is also better in the case of the dishwasher. The takeaways from our study goes as follow. First, in most cases, actually 19 of 24 experiments performed, the two-dimensional representation provides better performance than the one-dimensional pipeline, especially the Gramian angular summation field that outperformed the two other algorithms considered in our experiments. Though the recurrence plot is also a viable alternative in some cases, as it was demonstrated in the results section. During the evaluation process and the experiments, we noticed that the two-dimensional representation suffers from some limitations related to the computational complexity. However, we suspect that enabling the two-dimensional representation only for sequences with major variations would help to face this limitation. At the end of our presentation, we include a list of references that we relied on during our study for more curious and interested readers. We thank you very much for your attention and kindly invite you to read our paper for more details about our work.